In this video, we will be looking at question number 8 from the 4.6 homework. A count in a bacteria culture was 900 after 15 minutes and 1100 after 30 minutes. Assuming the count grows exponentially, what was the initial size of the culture? Find the doubling period, find the population after 65 minutes, and then we want to find when will the population reach 11,000. So based on this problem, there are a lot of ways we can go about it, but one way that's going to save us a little bit of time is going to be thinking about this in a way a little bit different than normal. I am going to let x represent the number of minutes after the 15-minute mark. That way I can think of this as 0 minutes after 15, we have 900 in our culture. And then the next one said after 30 minutes, we have 1100, but 30 is 15 minutes later, and we have 1100. So what they gave to me was after 15 minutes and after 30 minutes, but I moved it so that I can think of it as number of minutes after the 15-minute mark. That way I have 0 as one of my x values. We're assuming that this count grows exponentially, so we know we're working with something that looks like y equals ab to the x power. I'm going to plug in my first point, so we get 900 equals ab to the 0, but b to the 0 is just 1, so we get a is equal to 900. Now I can use my second point to find b. So 1100 equals a, which we said is 900, times b raised to the 15. If I divide both sides by 900, then I get 1100 over 900, which simplifies to 11/9, is equal to b to the 15th power. And to solve for b, I need to raise both sides to the 1/15th power, and I get b is equal to 11/9 raised to the 1/15th power. I could take that to a decimal, but I don't want to round if I don't have to, so I'm going to leave it just like this. So that means my equation is going to be y equals, my a value is 900, times my b value, 11/9 raised to the, 1/15. And that is raised to the x power. But when I have power raised to power, then I multiply them. So really I can write this as y equals 900 times 11/9 raised to the x over 15. That's the equation I'm going to be using, and I have to remember that x is the number of minutes after the 15-minute mark. So the first question asked, what was the initial size of the culture? You want to say 900 because that's what we used before, but that's at the 15-minute mark. I want to go 15 minutes in the past, so I'm going to plug in a time x of -15. So I want to go back in time 15 minutes. If I do that, then I get that our amount is equal to 900 times 11/9 raised to the -15 over 15. I'm going to break out my calculator, and we get 900 times 11/9 raised to the power of -15 divided by 15. And I'm getting 736 and stuff. So I'll say 736.3636 because 4 decimal places is usually pretty safe. For the second question, we want to find the doubling period. Now, the thing is about doubling periods is it doesn't matter where you start, you just want to double what you have. So right now, I'm quote unquote starting with 900. So I want to figure out how long it takes to get to double that, or 1800. So 1800 will be equal to the 900 times 11 ninths raised to the x over 15, and I want to solve for x because x is my time. I'm going to divide both sides by 900, and that will give me 2 equals 11 ninths raised to the x over 15. I can take the log of both sides, so that the log of 2 is equal to the log of 11 ninths raised to the x over 15 power. But I can use Amanda's favorite log rule, or the exponent rule to bring this x over 15 out front, so that I have the log of 2 is equal to x over 15 times the log of 11 ninths. I can multiply both sides by 15, so that we have 15 times the log of 2 is equal to x times the log of 11 ninths. And then I divide both sides by by the log of 11 ninths. I get x is equal to 15 times the log of 2 divided by the log of 11 ninths. When you do these complicated problems in the calculator, you can either do the numerator first and hit enter, then divide by the denominator, or you can put your numerator in parentheses and your denominator in parentheses. So I'll have 15 times the log of 2 divided by the log of 11 ninths. I'm looking at 51.8123. So it's going to take 51.8123 minutes for the bacteria to double. Again, it doesn't matter where you start, it just wherever you are, it's going to take another 51.8123 minutes for it to double from there. Next up, we want to find the population after 65 minutes. So you want to just plug in x equals 65, but we can't, because remember, x is the number of minutes after the 15-minute mark. So what we really want is 65 minutes, which is 50 minutes after the 15-minute mark. So that means I need to plug in x equals 50. So y will be equal to 900 times 11 ninths raised to the 50 over 15. And 900 times 11 ninths raised to the 50 over 15 looks like 1756.8840. And finally, we want to know, when will the population reach 11,000? So I'm going to start by copying over this equation so I don't lose it, because I ran out of paper. So we had y is equal to 900 times 11 ninths raised to the x over 15, where x is the number of minutes after 15. We want to know when this population will reach 11,000. So we will have 11,000 is equal to 900 times 11 ninths raised to the x over 15. I can divide both sides by 900, and that'll give us 11,000 over 900 is equal to 11 ninths raised to the x over 15 power. I can take the log of both sides, so we get the log of, this fraction reduces to 110 over 9, and that's equal to the log of 11 ninths raised to the x over 15 power. But that exponent can move out front, so that we have the log of 110 over 9 is equal to x over 15 times the log of 11 ninths. If I multiply both sides by 15, we get 15 times the log of 110 over 9 is equal to x times the log of 11 ninths. And then dividing by the log of 11/9, we get x is equal to 15 times the log of 110/9 divided by the log of 11/9. So if we type that in, we have 15 times the log of 110/9 divided by the log of 11/9. And I'm getting 187.1167 for x. X is the number of minutes after 15, so we need to add 15 minutes to this. And that's going to give us 202.1167 minutes. So a question you might be asking yourself is, why did we add 15 minutes to this problem, but not the doubling period? So this fourth part was asking when the population will reach 11,000. With the equation we used, we were thinking of the beginning at 15 minutes. So we needed to add the original 15 minutes that this bacteria population was already growing. Whereas for the second part, when we were talking about the doubling period, we don't care where we start, we just want to know how long it takes to double. So that's why we added the 15 to the last part, but not to the second part.